Hey, Bismillahirrahmanirrahim. And the topic we are going to study today is minimum total potential energy formulation. It is one of the methods of FEA which we apply to find the solution of different types of problem. For example, deformation in structural problems and temperature and heat and mass transfer problems. So we will learn how to use this process. It is an approximate method. हम अभी तक हमने जो है वो दो मेथड्स देखे पहले इससे. वन वाज द डायरेक्ट मेथड, उसके बाद हमने वेटेड रेजिडुअल मेथड देखा. नाउ दिस इज द थर्ड मेथड टू सॉल्व द प्रॉब्लम बाय FEA. सो ये होता क्या है, व्हाट इज मिनिमम टोटल पोटेंशियल एनर्जी फॉर्मुलेशन. उससे पहले हम देखेंगे व्हाट इज पोटेंशियल एनर्जी. सो पोटेंशियल एनर्जी is the difference between the total strain energy and the work done by the external forces. The strain energy is the energy stored in a material when it is elastically deformed, and some work is done in deforming an object. So the difference between these two, the strain energy and the work done, is the potential energy of the system or the body. So the mathematical equation for this, it is the symbol is for potential energy. So potential energy equal to total strain energy minus the sum of the work done. जितना भी हमने work done किया है, right? So this is equal to, so इसमें we have this is equal to the total potential energy. That is the strain energy, and this is the work done. So the strain energy, the work done, we know that work done is equal to the product of force and the deformation or the displacement. So in this we have the displacement or the deformation or the deflection in terms of u. हम इसको u की फॉर्म में लिखते हैं. तो हमारे पास जो w है उसकी जगह we have replaced it with force into deformation fu. So this is the equation for the total potential energy. Now in the next step, what we will do, we will minimize the potential energy. And how do we minimize a thing? We take a derivative of that thing and put it equal to 0. This is how we minimize a thing. So we will minimize the total potential energy by taking the derivative of the potential energy with respect to the deformation. So here we have taken the derivative of potential energy with respect to deformation, and we have put it equal to 0. So this has become the formula for the minimum total potential energy. So this is called minimum total potential energy formulation. We will find the displacement. So we will find the displacement when potential energy is at its minimum, right? So in this formula, we have two things. One is the strain energy, other is the work done. We will figure out both of them one by one. So we have strain energy. Strain energy, as I already told you, is the energy stored in a body when it is elastically deformed. We can find the strain energy with the help of these two graphs. So we have a graph of force and displacement, and we have a graph of stress with strain. So area under these two graphs will give us the strain energy, because we know that the product of force and displacement gives us the work done, which is sometimes equal to energy. So the area under this force displacement graph or the stress strain graph will give us the energy. So as it is a triangle, and we know that the area of a triangle is equal to 1/2 base into height. So from this 1/2, the height is f, base is x, so it will become 1/2 f into x. And we know that f is equal to kx. We also know that f is equal to kx from the springs. We know this. So we will put the value of f here, and it will become 1/2 kx into x, and the strain energy will become 1/2 kx square. So this is one of the formula for the strain energy. We will use another formula for strain energy. So here we have the other formula. in we have derived this formula from this graph. Area under the stress strain graph will also give us the strain energy. So one half of the base is strain and the height is stress. So we know that stress is equal to modulus of elasticity into strain. So it will become 1 over 2 E into E square. So this was for a small portion. If we take for the whole volume, so the sum of all the strain energies will be the integration over the entire volume. So the integration over entire volume will give us the total strain energy of the problem. And the second thing in this formula, that is the work done, it will be calculated by force multiplied by the displacement. When we will do the problem, I'll show you how we will find the work done by the external force. So let's move towards the problem. Here we have the problem. In this problem, we have to solve we have to find the deflection in the spring. The spring is with a spring constant of 60 pound per inch. There are two forces, one at the center which is 6 pound and the other is 35 pound. And we have to find the deflection. We are going to find the deflection by two methods. First, we will find it by the method of statics, and secondly, we will find it by minimum total potential energy formulation. And then we will compare the answers of both of the methods. First of all, we will draw the free body diagram. So here we have the free body diagram for this figure, in which we have 6 pound force at the middle, then we have 35 pound force, and the spring has replaced with the force of the spring Fs, and we have the reactions at the point where it has a pin. So first of all, we will solve it by the method of statics. Method of statics. So here we have the free body diagram. In the method of statics, we apply the equations of equilibrium. And what are the equations of equilibrium? One of the equations is sigma, sum of all the movements across a point is equal to 0. For example, let's talk about a point. Sum of all the movements about a point. So we have the force 6 pound force, and the distance of the 6 pound force from A is 5. We have 35 pound force. Distance of this 35 pound force from A is 6. We have this Fs force. Distance of this Fs force from point A is 8. So here we have the calculations. The moment due to the 6 pound force will be clockwise, so we have negative sign with it. The moment due to 35 pound force is also clockwise, so we will also have a negative sign with it. A moment due to Fs force will be anti-clockwise, so we have a positive sign with it, and these are the distances. So here we will multiply it and we get the value of Fs, which is equal to 30 pounds. So we got the value of the force, which is here, which is the force in the spring. We want to find the deflection. What we want to find in this problem is this. We have to find the deflection in the spring. Okay. So the value of Fs is 30 pound we have calculated. So we know the value of K. We know this formula, F is equal to Kx. So we know the value of K, which is 60 pound per inch. We got the value of force 30. So from here we can calculate the deflection, which will be equal to 30 over 60. So it is equal to 0.5 inch. So this is how we have calculated the deflection by the method of statics. So we are going to solve the same problem by minimum total potential energy formulation. So this is the original beam, and this is the deflection of the beam. It has deflected x distance at where there was a spring, and where there was 35 pound force, it has deflected xb distance, and where there was a 6 pound force, it has deflected an xg distance. So these are the distances of these forces from point A. These are the three distances. So we have the equation for minimum total potential energy, which we have learned earlier. So this is the equation for minimum total potential energy formulation. So first of all, in this we will find the strain energy. So strain energy we know that is equal to 1 over 2 kx square. The value of k is 60. So the strain energy will be equal to 30x square. Now in this problem, we will find the work done by the external forces. So we know that there are two external forces. One was 6 pound force and other was 35 pound force. So we know that the work done is equal to force into its displacement. So 6 pound into xg will be the work done. 6 pound into xg as written above, and 35 pound into xb is the work done by this 35 pound force. So this is the work done by the external forces. So we do not know what is the value of xg, we do not know what is the value of xb, but we can write these two in the terms of x by using the similar triangles. So you can see that we can make this triangles as similar triangles. So this small triangle in which this length is 5 and this side is xg, similarly this length is 6, this length is xb, this length was 8 and this length is x. So we can compare these triangles. So if we compare this triangle, let me number them 1 2 3. So in this triangle number 3, x over 8 will be equal to xb over 6. Here we have written. So here we got the value of xb. So in this triangle, triangle 3, x over 8 is equal to, with triangle 1, if we compare triangle 3 with triangle 1, x over 8 will be equal to xg over 5. Here I have written. So we get the value of xg from here, which is 5 by 8x. So I will put it side, and here we will get here we will put the values of xg and xb in this problem, and we will simplify it. After simplifying, we get the value of the work done. So this is the work done. Now we will do what we will do is we will again use the equation of the potential energy equal to the strain energy plus work done. The value of strain energy which we got was 30x square, and the value of work done is 30x. So we will now what we will do, we will minimize it by taking the derivative. We have taken the derivative with respect to x. So the derivative of x square and 3x, you will take the derivative of these terms, and here we have taken the derivative of 30x square, which is the derivative of x square will be 2x, so it will become 30 into 2x. Derivative of x is 1 minus 30 into 1, and we will put it equal to 0 to minimize this total potential energy. So from here we got the value of deformation